just done lots of calculations involving arc length. And if you think back to section 8.2 in our textbook, that was about arc length. And arc length was one of the big things that we did there. And the other thing that we did in that section was surface areas of solids that are formed by revolving a curve around an axis. And so unsurprisingly, we're going to finish this section by also thinking about surface area when we take a curve, parametrically defined, and rotate it about an axis. So let's read this theorem here, that C of t is x of t comma y of t. We want y of t to be non-negative. We want x of t to be increasing. That's just there to make sure the curve doesn't double back on itself. And x prime of t and y prime of t are continuous. Then the surface area we obtain by rotating C of t about the x-axis for t is between a and b has surface area. S is 2 pi times the integral from a to b of y of t times the square root of x prime of t squared plus y prime of t squared dt. So I'm not going to formally derive this, but I will say that this should feel very familiar. It's not exactly the same thing as we did back in section 8.2, but there are many of the same features. So back in section 8.2, let me just copy what that formula was. S was 2 pi times the integral from a to b of y of x times square root of 1 plus y prime of x squared dx. So these two formulas have many of the same features. 2 pi, integral from a to b, a factor of y, which is representing the height of our curve, times a square root, and there's things squared under our square root. And in fact, I can actually, so I said I'm not formally driving this, but as it turns out, this formula, the one we had back in section 8.2, is a special case of the formula that we're looking at right now. So if we were to set x of t to be equal just to t, that would mean that x prime of t would equal 1, and we would end up with, plugging things in here, we would have 2 pi times the integral from a to b of y of t times the square root of 1 squared plus y prime of t squared dt. But if x of t is equal to t, that says that x and t are the same. So everywhere we see a t, we can replace it with an x. And so we can do that. Of course, if we want to replace y of x with f of x, we can certainly do that. But here we see the theorem that we had back in section 8.2. That formula is just a special case of this formula. So now we're going to start doing something that looks like this. Same thing as before. Here's a parametrically defined curve, and we'll rotate around, and let's find the surface area. Okay, so let's do an example of this. So calculate the surface area of the surface obtained by rotating a parametric curve. C of t is t, comma, t cubed, about the x-axis for t is between 0 and 1. The picture looks something like this here. So what do we need? We see we need x prime of t and y prime of t. So x prime of t is equal to 1. Y prime of t is equal to 3t squared. And so we can now just simply write down our integral. 2 pi times the integral from 0 to 1 of y of t is t cubed times the square root of x prime of t squared plus y prime of t squared. Okay, so this is our integral that we care about. let us expand this out. 1 plus, that will be a 9t to the 4th dt. And how do we evaluate this integral? Well, let's observe here that if we take the derivative of the t to the 4th here, we get something times t cubed. So this suggests substitution. So substitute, if we substitute in u is 1 plus 9t to the 4th, du would be 36 t cubed dt. So du over 36 would be t cubed dt. Okay, what else do we have to do? We need to change our bounds. So when t is 0 and t is 1, when t is 0, u of 0 is 1 plus 9 times 0 squared is 1. When t is 1, u of 1 is 1 plus 9 is 10. So our answer is going to be 2 pi times 1 over 36 times the integral from 1 to 10 of, so this will be just becomes du, and we're just left with the square root of u. So crunching all of this out, we get pi over 18 times u to the 3/2, divide by 3/2, multiply by 2/3, plug in 1 and 10, and so you end up with, after simplifying, pi over 27 times 10 to the 3/2 minus 1. Okay, so that is an example of calculating out surface area when we revolve our parametrically defined curves about an axis. And let's end the section with our second pre-class problem. So all I want you to do is set up. You don't have to evaluate. Just set up an integral to obtain the surface area that you get by revolving the following curve about the x-axis. X is 1 plus e to the 2t, and y is t cubed.